Okay, this is lecture 41, lectures on embedded maximality by Harvey Friedman, please.
Thank you. All right, so things have gotten polished and written better and so forth. And I'm not quite finished with this chapter for putting it on the website in full form, but I think this will be my plan is this is the last lecture I'm going to give on this chapter. And because there's nothing all that new that's missing here. Um, and The plan is, I believe, I'm either going to talk about chapter 2, embeddings of real point sets, or chapter 5, finite incompleteness. Uh, I'm not sure which. Uh, Depends on what happens, but we're going to do 2 or 5 next time, and then 3 will be 4 is already on my downloadable manuscripts page, and this one will go on the downloadable manuscripts page sometime before next week. Uh, so we're moving along here, and so let's go through this today. I'll try not to be too repetitious from last week because, you know, it's been tweaked from there. Uh, and this is all the same. This is that background stuff. How about the same font? Oops. Yeah. If that's my biggest problem, I think I'm in good shape having those two O's look the same. All right. We have maximality without embeddings in the chapter on the pure math chapter 2. We haven't talked about for a long time. We have embeddings without maximality. We start here with maximality without embeddings, and then we go to maximality with embeddings, i.e. embedded maximality. And this is all elementary stuff that's been around a long time. Embedded maximality and usability. I did a little polishing here. Okay, the most basic usability of all, which comes easily from Ramsey's theorem. And then usability in one dimension is completely solved. Some background stuff about usability is stable. And two necessary conditions that's been around a long time. This dimension thing has been around a long time, and I wrote it out. This time it's written out. We don't need to talk about this much. It's straightforward. Then there's this whole chapter on finite usability that's been around for a long time, completely analyzing what the finite usable functions are with the theorem called fin use, which completely characterizes simply what the finite functions are that are usable. Usability being the point of the subject, what's usable. Then we go beyond the finite, as we did before, a little more polished. Identity extension usability and weak identity extension usability. And those are very closely related. But this one is at the level of large cardinals. This one here is the first 361 is at the level of large cardinals, and 362 is at the level of Zermelo's set theory. So you have a catastrophic drop in strength coming from removing a singularity. So this is very cute. My new way of talking about this step up or this step down between the weak one and the regular one. And then we have some variants, but not many. We have basically one variant. Yeah, we have two variants that are important, which are really just calibrations, two calibrations which are important. And then we have two uh, technical variants, two technical variants that are not the main event, but are used in the proofs because it's much more convenient to deal with them. And then we show their equivalent. Uh, Now, this is something I don't remember I had this last time or not. Order theoretic usability. So I want a general theorem that usability is implicitly pi 0, 1. I want a general theorem that usability is implicitly pi 0, 1 that applies not only to the functions that I work with in the detailed proofs, but for any order theoretic function, this is implicitly pi 0, 1. And what order theoretic functions are usable is stated to be beyond the scope of the book. That's the one of the main uh, research uh, programs to be done after this book. And I believe that the order theoretic functions can be completely analyzed as to what I conjecture as to whether they're usable or not, and blah, blah, blah. Okay. That's part of the future research. By the way, I might next week just talk about future research on this chapter somewhat briefly, maybe like 10 minutes or something. I might want to do that because that's something we haven't really discussed, and I haven't fully organized it, how I want to talk about the big conjectures and the programs. Yeah, programmatic something stuff. I may want to do that before going on to the other chapters. All right. So usability is implicitly pi 0, 1, even for order theoretic functions. Uh, okay. Then this is two trivial cases where the dimension is 1 uh, uh, or the size or the cardinality of the field, that is, or the size of the function is 1, which means it's the identity is an identity function, of course. These are actually trivial. This one's not as trivial. This one requires you to analyze what the one-dimensional order invariant relations look like. They're two-dimensional. The order invariant relations on uh, on the interval squared, on pairs. And that's been around for a long time. These are very simple. There's like 8 of them. That's why this is trivial. There's 8 simple ones. That's why this here is easy. Now, um, this is organized now. I think maybe I talked about this last time, but it's done better now. It's organized where there's a common in all my IEU theorems. These are the trivial IEU theorems. That means identity extension usability. Identity extension usability. That's what IEU means. In all those theorems that I do, there's really 4 of them. You'll see that there's 6 of them actually. If you include these trivial ones, if you don't include these trivial ones, it's 4. They all have a very, very common part of the proof. That common part of the proof doesn't have any special combinatorics of the cardinal that you use. Does not. And then you plug in the combinatorics that you use for the cardinal, and you get these different results with different combinatorics. So I've separated the combinatorics out, and that's what this is about. This is separating the combinatorics out all the way down here, down to here. Yeah. That's all separating the combinatorics out. And then the combinatorics is plugged in. The combinatorics is plugged in to here and here. the combinatorics is needed to figure out what these lambdas are supposed to be. How strong are these indiscernibles? And here is how they're used. So 5 and 6 are not really here, but they're placeholders. These are placeholders for the combinatorics that gets plugged in. See, the combinatorics gets plugged in here. And so here are the two of the main four is when the dimension is 2 or the field size is 2. And it's the combinatorics of omega 1 that's used. The combinatorics of omega 1 is sufficient. For the other two, we have large cardinal combinatorics has to be plugged in. Large cardinal combinatorics has to be plugged in. And we have k and n bigger than or equal to 3 here because we already handled 2 and 1. 1 is trivial, if you remember. We already handled 2. So that's why I say k greater than or equal to 3. And, you want 1 subtle if k is 3, right? Okay, so that's how all that stuff is done with the IEU. And the WIEU means weak identity extension usability, weak. I redo this without combinatorics because it's very similar to the IEU development without combinatorics, but I didn't find it convenient to exploit the fact that they are the same, except very close to each other, except in the development here, I say, oh, this is like that one before, or this is exactly the same as that one before. Some of this stuff is exactly the same as that one before, you see. So, but I just sort of formally redo it uh, without necessarily having redo all the material, but I redo all the sections. If you see the sections are the same, except I write lambda 1 through lambda n instead of lambda 0 through lambda n minus 1. There's a reason for that. It's more suggestive to do this. We don't have to get into that technicality right now. Okay, and then these are from 1 divided by n to n divided by n, whereas the other stuff, this is the weak stuff. The strong stuff is with 0 over n all the way, 0 over n minus 1, all the way to n minus 1 over n minus 1. You see. The other one starts with 0 for the function. All right. I don't know how much sense this makes for you, but some sense. And then the combinatorics, before we had a section on the large cardinal combinatorics, here we have the iterated exponential combinatorics that we plug in. And that combinatorics is the Erdős-Radó combinatorics. It's the combinatorics that sits in Z, Zermelo set theory. In other words, iterating the exponential function starting with omega, or iterating power sets, iterating it finitely many times. Yeah. So we have this statement. There's no point in doing 2 here because the weak one and the strong one, they have the same situation basically for 2. So before we have this stuff with 2, it's not important here. Okay, so here we get k minus 2 iterated exponentiation. I don't fear that k is 2, 1, or 0. No, k in this book, k is, unless I stated otherwise, is a positive natural number. I don't fear k equals 1 or 2 because by convention, x sub 0 and x sub minus 1 at omega is just omega. Okay, so that's why I don't need to put in anything here about k greater than or equal to 3 or whatever. Okay, don't have to do that. Okay, so then, And then I consolidate everything uh, in neater form. First of all, there's full IEU, which is for all K and for all N. There's full IEU and there's full WIEU. And I just read off what the obvious results are for that from what I did here. And then instead of doing double cases, you can actually talk about min of K minus 2, N minus 2 subtle. So you can get away with this kind of cardinal, and you can get away with this kind of cardinal instead of splitting. You can use the min. Okay. And then I have a section on what exactly are the formal systems that I want to say are enough to prove these various things, and just to be precise, because I'm using informal language. I'm saying using something. I'm using omega one. So I want to get more formal, and then I do that here. So there's two ways to be more formal. One is which set theories or regular standard systems, which maybe I should say in standard theories. Uh, yeah, that's what I really want to say. In standard theories. Uh, which standard theories, because I'm going to be looking at the Z3, for example, which is most people don't call it set theory, third order arithmetic, something like that. So I say in standard theories, and then from consistency statements. So in general, with this kind of situation, if a theory works to prove it, then con of that theory, EFA plus con of that theory is enough to prove it. And that's because the statements are implicitly pi 0, 1. The statements are implicitly pi 0, 1. That's why you can go from a standard theory doing it, proving it, to a consistency of a standard theory plus EFA. You need some background proving it. So that's what goes on in 319. See, everything's more polished than last week. Then I talk about graphs and emulators. I really do need graphs because graphs are where the reversal is, and I'm not going to change the reversal. And in some ways, you can argue that having graphs is a little better for the reversal, although that's a little bit of probably a lie. But anyways, this is the way it is, and I'm not going to be changing it away from graphs. There's nothing wrong with graphs. So, and also graphs are intrinsically important. So I talk about graphs and emulators, and usability is based on chains. Now we have usability for graphs, as you shall see, and we have usability for emulators. The same usability concept, basically, that you can use it for maximal things. So that's nice and unified. And then we have a theorem, which I'm not sure it's true in complete generality. This is where I didn't finish. That usability for graphs, usability without any adjectives is usability for chains. So that usability for graphs, usability for emulators, and usability for chains, i.e. usability, are all equivalent. That might be a slight fib, but I think it's true. I haven't actually. There were some if, ands, and buts in a different version of this chapter that had more material in it than it ought to. But with this particular neat form of chapter 3, I think it's true that usability is the same for graphs and emulators and chains. And also K usability is the same. K usability might be slightly different, particularly for K equals 1. But full usability for graphs and emulators and chains are probably equivalent, and that's very nice to have. Then we derive this statement. This is the current lettering for it. We derive this statement that's been reversed. We derive this statement that's been reversed, which is really basically the same as the usability for graphs, that is, the usability of this function. This is a notation for a particular function that falls well within all this theory that we did earlier, well within the with the IEU, with the lead statements of invariant of embedded maximality. Um, so we get the derivation of this very neatly and simply. And then we know that we have reversals of the main statements because of this. Of course, this is reversed not in this chapter, but in chapter 4. Then we have further investigations. There's a lot of red meat in there we got to do. Talk about that. I'll talk about next time. Okay, I'm committed to talk about this next time. It'll be a nice talk because I don't have to prove anything. I just have to talk about future proofs of things. All right, so this is all the same. This is all the same. In chapter 2, we have embedding without maximality. Here we have maximality without embedding, which is all background stuff. And then we get uh, real stuff. This is a subsection, maximal chains and relations, maximal chains and order invariant relations. Yeah, that's just a subsection. All right, and then the book really starts here, uh, which we've been over before. Partial function, that's a double colon. Embedded, what does it mean to be F embedded? We talked about this, hasn't changed. Usability means that F is usable if and only if every order invariant relation on every -1K has an F embedded maximal chain. That means you can use it all the time. And K usability means you can do it use it all the time for K dimensions. Uh, Closure under inclusion is trivial. Here is the definition of the subject. Nice, simple definition of the subject. And we completed it for the finite ones and didn't use didn't use any serious hypotheses, no set theory of any kind. I think we needed SIFA for this, super exponential function thing, because Ramsey's theorem with unlimited dimension comes in. By the way, if you want to do finite reverse math, then there are some issues. What about reversals in here? You see, I mean that kind of stuff goes into the chapter called section 22 called further investigations, finite reverse math study of this, or something. All right. So now I think maybe this is only streamlined. Maybe I filled in the proof. Yeah, so you won't see any difference. But I did fill in the proof in detail for this. Strictly increasing is important. That's necessary. So the most basic usability theorem is every strictly increasing finite function contained in the open interval 0, 1 squared is usable. And this of course is a special case of the complete analysis of the finite usable functions, of course. But this is done early and easily right away, without getting into that involved chapter. Okay, and it's just really Ramsey's theorem comes out of Ramsey's theorem, but you have to be careful about the fact you have to use very strongly the fact that everything is order theoretic here, except for the endpoints. That's why the endpoints are not in here, because it's not true. It's not true, and this is not true with closed 0, 1. Um, this is a slight modification of this proved the same way. Uh, and it's actually true if you fix just one endpoint, but that's more involved, and that gets into the serious stuff called fin use. One usability is for any function, doesn't have to be finite, and uh, it's very easy to be one usable. So I have, yeah. So there's a bunch of, okay. So the theorem, the one usability theorem is either the field isn't everything, or F has a fixed point. Uh, all right, then there's a bunch of background material about usability being closed under composition, closed under inverse in a certain sense, and also closed under isomorphisms, as long as those isomorphisms preserve the endpoints minus one, one. So all that background material is useful. This is a minus of F. That means you can reverse the order of everything and everything comes out nicely. Two necessary conditions. Strict increasing is super important. So a necessary condition. Yeah, I don't know why this is here. I don't know. No, I'm not going to worry about it. All right. So strictly increasing, strictly regressive, strictly dominating, that comes up in the section analyzing the finite usability. Even if it's just two usable, it's strictly increasing. That's not true for one usable, though. And also this, you can't have this obstruction. This is an obstruction, this fundamental obstruction. And on finite usability, here's the theorem. These are equivalent. Usable, two usable is the same. Strictly increasing and avoiding that configuration is the same. This is all the same. And then there's a corollary. F is usable if and only if every two element restriction is two usable. And you can get that from this. Now we get into large cardinals. Okay, so it's called identity. So if we go very modestly beyond finite usability, we run squarely into ZFC incompleteness, and it's convenient to treat F as a set of ordered pairs. You treat these functions as a set of ordered pairs. IEU, identity extension usability. If strictly increasing F, and I use the set of ordered pairs notation, it's very convenient, is finite, then F union the identity function up to zero and not including it is usable. If strictly increasing F contained in 0, 1 squared is finite, then F union ID of minus 1, 0 is usable. You know, I hate to do this, but I'm beginning to think that I can make this even neater English wise. What if I say if strictly increasing F union if the strictly increasing function F union ID minus 1, 0 is strictly increased, every strictly increasing, yes, you see, interesting because you can keep improving. Every finite strictly increasing function F union ID 0 is usable. See, this is the story of my life. I keep improving. Every strictly increasing function F union is usable. My gosh, I never thought I would never thought I would improve this so while I was talking on it. So I think that's the best. I mean, it's the same thing, but now look at the smooth English. Look at the smooth English. Oh, but it's not finite. Ah, got to be careful. Yeah. Okay. I take it back because this whole function is not finite. I can't play that game. Okay. Another story of my life. There are more wrong things I do than right. That's for sure. Ratio is 100 to 1. All right, identity extension usability. If strictly increasing F is finite, then F union is usable. Okay. All right. Strictly increasing is necessary. That's why that's there. Zero, you can replace zero in here with anything else, except if you replace it with one, it's trivial. If you replace it with -1, the statement is false. All right. Yeah. Okay. So large cardinals is needed to prove that. That's con SRP. Now the weak one, let's compare the weak one with the regular one that we just did. So look at this. They read exactly the same at first glance. There's no difference. But here's the difference. This is the closed unit interval, right? And this is the open unit interval, right? You see, and this one is Z and this one's large cardinals. All right. Okay. So what I've done is you notice that I've disallowed a singularity at zero. I've disallowed a singularity at zero because F is not defined at zero and it has no value at zero. See? Whereas over here, I have a singularity at zero is definitely going to come up because I have left bracket zero here. You see? So the singularity, so this is very good mathematically. The singularity is causing an explosion in strength. That's very suggestive. Like in mathematics, singularities cause other kinds of explosions, right? This is an explosion in strength, allowing a singularity at zero. All right. So we have this. This is actually provable in Z. And probably not less. That's a reversal issue. We believe there's no proof in ZFC with power set replaced by the scheme V omega plus N exists for every N. All right. We conjecture that. We discuss that in future investigations. Now, on the informative side, we simply have calibration. Here's the calibrated form, IEUKN, where K and N are fixed. If strictly increasing F has N element field, then the function is K usable. So that's what that means. And we can calibrate this one also. Same kind of calibration idea. And then there's technical variance. The technical variance amount to these amount to fixing these amount to specifying the field. See? That's what this amounts to. And that, by the way, makes the proofs it's a little bit easier and clearer what's going on. In fact, when we do this, we make sure we have the singularity at zero. All right, and that's it. There's nothing else. No other notation. So IEU and WIEU are the lead statements. The calibrated lead statements are IEUKN and WIEUKN. The IEU prime and the WIEU prime are the technical variants that we actually use, but they're not the main event. And we prove the equivalence. There is a little bit of an annoying thing, but it doesn't seem to have any real effect on the results. Uh, at least right now, I don't see. I think not. Namely, that I need ACA not to give a soft proof, to give a elementary proof that these are equivalent, and these are equivalent. Uh, and these are equivalent. This is obvious. It's just calibration. But there is a problem going from IEU prime to back to IEU. I have to extend a I have to extend a maximal chain, a chain to a maximal chain. I have to extend that, and that in general that requires ACA not and not well, just requires ACA not to do that. Yeah. All right. Now, order theoretic usability is just usability applied to order theoretic functions. So there's some discussion of what the order theoretic sets and the order theoretic functions are. That's from this earlier chapter, section 3.2, that's background material. It's just so I restate some of the background material for that. And we have this very robust notion of order theoretic, which is the same as first order definable over the Q less than. And then we have characterizations of the order theoretic functions of one variable. The order theoretic functions of one variable have a very basic, important description uh, from O minimality theory. Uh, in higher dimensions, it gets more and more involved, but in one dimension, i.e., contained in J squared, where J is an interval, well, minus 1, 1 for us, uh, has a very nice description. All right, we don't really need to get into it. All right, so then I talk about, as this has been around for a long time, the notion of implicitly pi 0, 1 and how that is almost the same as falsifiability, and how falsifiability is important in science. It should be important in math. It just means like pi 0, 1, except it may not be in that form. So then we have that usability is implicitly pi 0, 1 for order theoretic functions. See here. Okay. Uh, yeah, so we have I don't know, I didn't, I should have formatted this with the Greek letters, but the idea is that uh, having an invariant maximal chain for an R, having it not invariant, embedded, an F embedded maximal, R having an F embedded maximal chain, uh, where R is k-dimensional, is actually a pi 0 1 sentence. It's actually of this form. And then you can use that to argue that all of this stuff is pi 0 1. It's from implicitly pi 0 1. Everything in sight is implicitly pi 0 1. Now, these are trivial, as I said. Then we have this section of IEU without combinatorics. And remember, in the way we do this with the primes, with the technical thing, the field is fixed. The function is fixed. All right, so yeah, so we start with that. Then we always put it on. We always go to the transfinite. This particular transfinite object, where kappa is the cardinal that we're going to use, and then we put O-rings on them. So we've done this a lot, and we pick a uncountable regular cardinal, not specified. How strong the cardinal is tells us how strong our result is going to be because of what kind of combinatorics we can get out of it. In the weakest case, kappa is omega 1. And then we put the obvious ordering on it, and then we on this, and then we put the well ordering on this. So we can actually do transfinite recursion. And that's how we build the inductive chain. This is the greedy construction of the inductive chain. Okay. And then this stuff tells you how to wholesale lift various things from the rationals into transfinite. All right. So here's the transfinite recursion. X and WK lies in the inductive chain, if and only if when you take what you've got so far and add it on, it's still a chain. It's called inductive chain, uniquely defined. And it's actually a maximal chain, but it's maximal in each restriction. If you restrict it, it's maximal there. That's what the greedy stuff does for you, by the way. Then we associate a closed unbounded E. I think we talked about this last time. And we have E lifting. So this is a closed unbounded set that you pick, which saves a dimension, actually. It's very important from that point of view. Well, I do what amounts to a special case of Gödel collapsing. So I finally get down to E lifting. E lifting says if alpha is less than beta are both from E, this closed unbounded set. And if you have X and Y, if you have X whose maximum whose maximum coordinate is in E, then you can lift it to a higher let Y be the result. We're replacing max of X in y, by Y. Okay, this is all screwed up. By replacing, okay, I said this wrong. What I mean is if the max is alpha, and you then you can replace alpha by beta and get a bigger max, then you don't change the truth value of this. How did I screw this up? Um, equals alpha equals alpha. And why be the result of replacing uh, alpha in X by beta? Okay. Then the truth value has not changed. So that's called E-lifting. That's used a lot to keep the dimensions from growing too much. And then we pick ordinals according to the combinatorics that we're doing. The combinatorics that we're doing rules what cardinal we pick and what indiscernibility properties these have. But no matter what, we take we're in the transfinite. We take f star to be this, and uh, and then we take f star to be this map, which is a unique map, so that it's isomorphic to our original function. Our original function. You see? So we've now lifted the whole problem up to the transfinite. We solved the problem. Getting an embedded maximal chain. We solved the problem in the transfinite, and then argue that that solves the problem in the original rationals by elementary extension, by using elementary substructure. So we claim to have solved the problem here, although this is a placeholder for the actual combinatorics. But that's what happens. And then we form the two structures. We just form these two structures. That's all I'm trying to say. The second one is an accountable elementary substructure of the first. The second one. And then we have an isomorphism from the countable elementary substructure onto some structure of this form. See, we can map these transfinite objects onto these rationals. And we don't know what S is, but S is going to be the solution to what we want. See, so we'll see what happens here. See, and then you finally get the embedded chain you want. Because of the S here, this is the embedded chain. So I've just black boxed the combinatorics and what exactly this cardinal is kappa that is doing all this work. That's black boxed. Okay, so you get this at the end. And then I apply this to omega 1 because the combinatorics of omega 1 is very basic. And you get this to work in dimension 2. Now, if you can also have the field be 2 and the dimension wild, but that's still, even though the dimension is wild, there's only two things it's playing around with. So you still get the same combinatorics, except it's cycled differently, so to speak. So you get this result. And then you have to do the large cardinal combinatorics, or the subtle cardinal hierarchy or SRP hierarchy. They're all intertwined to get more. So instead of 2 dimensions, for example, it's k dimensions, that kind of thing. So there is a piece of combinatorics that's really relevant that comes out of subtleness. Uh, if you have finitely many functions defined on a closed unbounded set, verity at most k, then you can find a set such that order equivalent things. It's like the homogeneous definition in large cardinal combinatorics. In other words, the intersection of the min xy is the same as the intersection of yeah, because it's sets now. This is mapping into sets. See, if we were mapping into ordinals, it would have to say regressive and being equal. But here we're talking about sets. Okay, and then this is a trivial restatement of this, where the ranges, where we control the number of elements of the different elements of the set of the tuples. And the difference here is that I'm getting away with an n subtle cardinal and not, I don't need a k subtle cardinal. I just need an n subtle cardinal with this. Um, okay. And then there's a variant of this where, yeah. Okay, so then you can use this. Okay, and this argument is very similar. So I plugged in the combinatorics. I know it gets a little tricky, a little complicated, but you'll see the polished manuscript if you want to get into it soon. Okay, and then I do it for WIEU. And basically, this is the same thing, except the singularity isn't there. And so the combinatorics become simpler. Uh, yeah, the constant parameters for the large cardinal combinatorics are now way down low and not even close to the where the indiscernibles are. Whereas before, the parameters of the indiscernibility, the parameters are go all the way, reach up all the way and don't touch, but reach up all the way to the first of the, all the way to the first indiscernible, so to speak. Yeah. Right. Okay. This is all as expected. The large cardinal combinatorics, is you don't use large cardinal combinatorics, use iterated exponential combinatorics with Erdős-Radó. That's why this stuff is weaker. But it's fairly involved and tedious to do this completely, which I have. So let's go past this. Here's where I want to get into exactly what formal systems are used. And this is pretty much as expected in standard. I changed that to in standard systems. Now, there is an issue here about, and here it is. Here's what I need. There is an issue here. I'm going to be taking a proof, the proof which I give, which uses that cardinal, that iterated exponential cardinal, and I want to replace this with a proof in a formal system of a standard kind. So it turns out that a min of k minus 2, n minus 2 iterated exponential, it corresponds to the system min of k plus 1, n plus 1. In other words, there's a jump of 3. So that means, that tells you why it's Z3 when k equals 2, or when n equals 2. All right. And then, so that standard systems are nth order arithmetic, and then Z and anyway, but you can also do it from consistency statements, because if you have any implicitly pi01 sentence proved in a system, then you could prove it equally well from con of that system with background EFA, here, EFA plus con T. And so therefore you get this result that all these things are proved from the con, except there's one thing that isn't you get too weak a result. It's not refined enough for this, which I do separately. IEU is provable in EFA plus con SRP. Okay, then we have graphs and emulators. I think you know what they are. We've talked about those. And then graphs and emulators, right? And as I suggested, so there's usability for graphs, which means F is usable for graphs, means every order invariant graph on every minus 1, 1 to the k has an F embedded maximal clique. That's what it means. And then for emulators, a similar thing. And then I think the 3 different definitions of usability, the straight out one, which is usability for chains, as I said, these things are equivalent, at least for 2 usability, at least full usability is, yeah. It may differ on dimension though. See, because I talk about usable graph / graph, usable / graph, emulator, usable. Well, maybe I didn't say it, but okay. Usable for emulator. Yeah, here it is. Okay, so I have it for emulator. Okay. I think that's it. That's all I prepared. So this is almost complete. Yeah, I didn't present here, but it's already around previously that the statements here easily prove the statement being reversed. Once you know that usable with emulator is the same as usable. That this is all matches perfectly. So we have the reversal in full that we want. Okay, so that's it. I'm done.